Okay, this is another topic that I'm not an expert on at all. This is more of chemical engineering and subsections of chemical engineering that you can talk to chemical engineers about, because in chemical engineering, you have process engineers and people who are experts at electrolyzing or whatever else. Okay, but why am I reporting it? Because I read it and it's a very interesting topic, and I think we should all be aware of this perspective, and it's very critical for the overall transition of the energy system as well as the entire manufacturing system. So we'll just kind of walk through it. There are a lot of details that I'm going to skip as usual, but I'll give you the most salient points according to my understanding. You can always go back and read the paper if you're interested in more details, and the experts can always write to me telling me if I missed something or misrepresented something, right? I'm saying that because there has been some complaint by one person that I cannot be covering so many topics. Well, I am, so that's life, right? Fossil fuels, coal, oil and gas supply most of the world's energy and also form the basis of many products essential for everyday life. Their use is the largest contributor to the carbon dioxide emissions that drive global climate change, prompting joint efforts to find renewable alternatives that might enable a carbon neutral society by as early as 2050. This number comes from basically looking at the linear relationship between accumulated CO2 and the warming rates, and then where we need to be if we want to hit something like 2 degrees C by 2100 with, let's say, 67% probability. Lots of scenarios there, but nonetheless, being carbon neutral by 2050 is a good goal. Are we going to get there? Well, we will try. There are clear paths for renewable electricity to replace fossil fuel based energy, but the transport fuels and chemicals produced in oil refineries will still be needed. So this is critical. You may phase out fossil fuels for energy production, but the transport fuels and chemicals produced in oil refineries will still be needed. So you will, resort to CCUS, carbon capture, and other methods. But here the perspective is on how the refineries themselves can be also part of the carbon neutral system. That's why I'm reporting on this with whatever little I could understand by reading it. So we can attempt to close the carbon cycle associated with their use by electrifying refinery processes, and by changing the raw materials that go into a refinery from fossil fuels to carbon dioxide for making hydrocarbon fuels, and to agricultural and municipal waste for making chemicals and polymers. So all kinds of thought processes are put in. We argue that with sufficient long-term commitment and support, the science and technology for such a completely fossil-free refinery delivering the products required after 2050, so less fuels, more chemicals, could be developed. This future refinery will require substantially larger areas and greater mineral resources than is the case at present, and critically depends on the capacity to generate large amounts of renewable energy for hydrogen production and carbon dioxide capture. And they look at technical challenges, economic challenges, societal commitment needed for the long term to make this happen, and so on and so forth. So let's read some main points. As I said, it's a long, nice perspective with lots of references. I'm going to keep it brief as usual. Population growth and the increasing consumption associated with a higher standard of living have led to increasing anthropogenic carbon dioxide emissions that cannot be absorbed by the natural geological and biological carbon cycle. So there will be irreducible emissions that need to be taken out. Negative emission technologies is what we keep calling them. Because these emissions change Earth's climate with adverse effects such as more frequent and severe droughts, heat waves and rainfall, he's not a climate scientist, but he's mentioning the main things. The aim is to reduce CO2 in the atmosphere by about 424 ppm in May 2023 as set out in the Paris Agreement and Kyoto Protocol. So we aim to reduce CO2 in the atmosphere as set out in the Paris Agreement and the Kyoto Protocol. Kyoto Protocol is dead and gone, a failure, but Paris Agreement is very much underway with the nationally determined contributions, and the CO2 concentration is jumping by about 4 ppm per year. So by the time I'm recording this paper came out in 24 and I'm recording it in October 24, almost at the end, and we must be now around 426, 427, something like this. Applicable to us is the European climate law, which provides a legal framework for the rapid reduction of CO2 emissions and targets an economy that is carbon neutral by 2050. Okay. Because a large fraction of current CO2 emissions arise from the production and use of energy, achieving this ambitious goal will probably involve an energy system based largely on renewable electricity, with a prominent role for solar photovoltaics and wind power. There are others: hydro, nuclear, wave energy, and so on, geothermal. But there are less obvious solutions for how to reduce the emissions of refineries, which at present process fossil-based resources to make our transport fuels, performance chemicals, and monomers for polymer production. Transport fuels, which are the main products of today's refineries and contribute about 25% of the present-day CO2 emissions, can in part be replaced through transport electrification, but electrification will not be feasible for all transport modes, and there will be an increasing demand or need for chemicals and polymers as both the world population and material needs of developing countries grow. Developing alternative carbon neutral refining concepts that focus on sustainability and circularity will thus be essential for transitioning towards a carbon neutral economy in 2050. The key questions that need to be answered for a carbon neutral refining concept are as follows. This is not oil drilling, coal mining. This is refining processes, refineries. So very specific. Okay. What carbon input will replace the fossil-based resources to enable a carbon neutral refinery? Can science and technology progress rapidly enough so that we can replace in time existing conversion processes with more sustainable alternatives? Are available energy, materials, and land resources sufficient for designing and constructing carbon neutral refineries? And what are the costs associated with building future refineries, and how can we make them economically and socially viable? So you need to account for other factors than just cost-benefit analysis. So in this perspective, we attempt to provide some answers to the questions above by sketching a possible roadmap towards a refinery of the future. So it's a scenario, possible roadmap, and obviously there will be a lot of responses, I'm sure, to this perspective, but it's a good start to discuss it especially for us who are climate scientists, or you may be some other related field that is watching this. We do this using order of magnitude calculations for a single refinery plant that we assume to be located in Europe, subject to European regulations. We first discuss the necessary building blocks for the anticipated refinery concept. We then evaluate the required land and offshore area, resources and investment costs, and consider the necessary scientific and technological developments that are needed to make this all possible. We also highlight some possible showstoppers, which include the need for large amounts of renewable energy and the so-called critical chemical elements to construct all the necessary hardware. So it's hardly a done deal. There are potential showstoppers, which means deal breakers, which means major barriers that may make things quite impossible. So obviously some schematics and some technical things that I will not be able to go into. I have read it, I understand most of it, but here is a refinery and here is electricity generation. So this is the anticipated refinery of 2050 compared with the refinery of 2020, where the baseline for this paper is. So you have oil 86%, other 14%. In 2020, you had 150,000 BPD. Uh, let's continue. Plastic waste, biomass, CO2. So 25%, 25%, and 50. So you have by 2050 81,000 BPD. So coming out here now in 2020 you have gasoline 43%, diesel, jet fuel, and other, including polymers and chemicals, whereas by 2050 you would want diesel and jet fuel, which haven't been phased out yet, polymers, which will be still very much in use, and chemicals that are still needed for various applications in real life. Okay, that will be barrels per day of 150,000 in 2020 and 81,000 by 2050. So obviously you are going to more than halve the amount that you are producing. So obviously you have transitioned by 2050 towards net zero. Maybe you have assumed achieved carbon neutrality, but these are the unavoidable refinery processes that are still needed. In terms of electricity generation in 2020, you have 26,745 terawatt hours, and also there is hydrogen generation, which I didn't mention, but we'll look at it. So hydrogen by 2050 you will jump to 71,135 terawatt hours. So here you have fossil fuel dominating, and you have some nuclear, hydropower is there, wind and solar and other are tiny fractions. Hydrogen is not showing up here in 2020, but by 2050 you will almost, well, not quite triple, but more than double the energy production in terawatt hours, and you will have much more, you would have reduced fossil fuel, you would have increased nuclear, and hydropower is still there, increased a little bit, and wind has jumped, solar has jumped, other, and hydrogen based. Sorry, I'm getting a phone call which is a Amazon delivery that I have to take, sorry. Okay, sorry about that. Let's continue here. So what else do we need? Electricity generation will mostly go to renewable, but fossil fuel will still be there, and this is of course optimistic scenario right now because we have not scaled up many things yet, but in the sense that are we really going to be able to reduce fossil fuel use for energy generation by so much? Okay, and hydrogen generation, again, it's now 2021 was at 94 million tons. In 2050, we expect that to jump to 528 million tons based on various calculations from the IEA that you can look at. And IEA is very optimistic about what will happen to fossil fuels and when we will hit peak emissions as well as peak fossil fuels, and somehow we are going to leave all that money in the ground, assets buried in the ground and so on. So gray H2, so gray, green, blue are basically how we do it. Green is where you are splitting water molecules, let's say, or some process to produce hydrogen using renewable energy. Blue is when you have some fossil fuel, I think, and you capture the CO2 that is produced in the process. Gray is where you are releasing some of the emissions by producing H2 with fossil fuels and so on. Okay, so you can read that elsewhere or listen to my podcasts elsewhere. So green H2 will dominate, but blue will also be there and gray will be small. These are the optimistic scenario, and this is the overview of the various conversion processes in the refinery of the future. So this is really nice, at least optimistic and fun to read, right? So H2O electrolysis, we already talked about the various green, blue and gray, and CO2 with direct air capture and carbon capture and utilization. So you are going to mix H2 and CO2 and produce some usable fuels, including methane, and you are going to produce some diesel and kerosene and lubes as well in the refinery of the future. There are all these processes that I'm not going to get into, and it will take biomass. Somewhere you are producing biomass, and the usual optimistic scenario is that you are using degraded lands so that you are not competing with food security, you are not competing for water and other things. So gasification, pyrolysis and depolymerization is going to happen. These are again energy intensive processes, but you are hopefully producing enough hydrogen and renewable energy, and you have reduced fossil fuel so that you can do this safely in a life cycle and circularity sense. So you're going to feed those into carbohydrate platform molecules, various processes to produce functional molecules for various applications. Plastic waste, which is now quite a nightmare all over the ocean, even in our body and blood and brain, breast milk and so on. We are going to do pyrolysis, high temperature closed reactions, and do depolymerization as well, and convert to naphtha range hydrocarbons to produce monomers for polymers. And we are going to take the byproducts here also to produce coke, and which will be used for asphalt, let's say for making roads. So it's a nice thought process, at least, right? So we don't have to be too pessimistic about it right now. It's a perspective. So the author is giving possibilities that are there, and a scenario for hydrocarbon fuels production processes in the refinery of the future. So you are going to use green energy, numbers given 7.3 gigawatts. 3.7 is going to go into electrolysis to produce hydrogen, so that will be green hydrogen, and you are going to put 1.5 gigawatts into DAC, and DAC is now by 2050 has scaled up nicely. And if we are running on green energy, then maybe it's not so important about how scaled up it is, that you can keep running it even if it's not capturing lots of them, lots of CO2. Remember, CO2 is at 0.04% concentration in the air, so you need to flow through a lot of air to precipitate out the CO2 from it. So you take some energy also now for electrolysis, and CO2 is put in to produce carbon monoxide, and combine with H2 to produce again hydrocarbons, jet fuel and so on. 5.6 kilotons per day, so 40,500 barrels per day. So I'm just being again very brief in these things. There are processes that are involved, that are chemical engineering topics that we will not bother about it, just to get an idea of where we are headed. And integration of the carbon streams in the refinery of the future. Feedstock CO2 coming in at something like 12 kilotons per day, biomass coming in at 8.2 kilotons per day, and plastic waste coming in at 3.8 kilotons per day. And you are going to take CO2 mole fraction, carbon and carbon coming from these, and produce CO2 and carbon, go into chemicals and materials. So chemicals and materials that will still be needed, as we said, and produce syngas and other fuels, which are also products coming out. So there are numbers on calculations done. So it's not a just a hand wavy argument, but of course a lot of assumptions. Whenever you make future scenarios, you have a lot of assumptions going on, right? So let's not worry too much about it, and let's look at the technical challenges that the author envisions. The steps that can be taken to decarbonize electricity production and a large part of the transport sector are relatively clear, but realizing the proposed 2050 refinery concept will be a more demanding task given the complexity of the feedstocks, processes and products that are involved, and considering the necessary process and technology innovations and scale up of existing technology that are still required. So it's a scenario, and that's how it works. Key technical challenges need to deliver. Technologies for CO2 direct air capture are required on a scale of approximately 20 kilotons per day for a single refinery. So imagine how many refineries there will be, but each unit can have this much by 2050. Electrocatalytic CO2 activation and conversion processes need to be efficient, selective, use earth abundant elements as catalysts, and ultimately produce molecules more complex than carbon monoxide at a scale of approximately 20 kilotons per day for a single refinery. Large scale reactors needed to be electrified to lower the CO2 footprint of endothermic production processes. Such process electrification might be compatible with existing refineries and could serve as an intermediate solution for lowering refinery CO2 emission. Electrocatalytic CO2 conversion and hydrogen production are both accompanied by oxygen formation at the anode, which should be replaced by reactions such as oxidation of molecules derived from agricultural and municipal waste that generate useful products such as biochar, I can imagine. Carbon efficient processes are needed for making chemicals from biomass and agricultural waste. And for recycling of plastic and municipal waste, this will require new catalytic technologies that should be based on earth abundant elements. You can go and read what they are. Considerable infrastructure needs to be developed to ensure sufficient solar PV and wind power generation capacity, so about 6 to 7 gigawatts per refinery. Effective and reliable energy storage techniques are needed to store excess energy during peak solar and wind power production to manage intermittency, which is a problem for all of us for renewables. Effective and reliable energy storage techniques are needed. Already said that. Green hydrogen generation capacity needs a substantial scale up to meet future refinery demand and be based on electrolyzer technology that uses stable electrodes composed of earth abundant elements. In the interim, H2 can be generated through processes such as biomethane pyrolysis. References are given there, and this yields solid carbon and thereby avoids CO2 emissions. So biopyrolysis in a closed chamber at high temperatures here produces H2, which can be taken out, but the remaining product is solid carbon, so it's like coal that it doesn't directly emit CO2 unless it's left out to weather and so on and so forth. Okay, so pretty amazing idea. As I said, technically quite complicated. I have managed to avoid the technical details that I don't understand, but hopefully given you enough sense of how people are thinking about every aspect of transitioning to net zero. And refineries are a big part of our life. Right now they are seen as massive emitters, so we have to keep them operating because they cannot be phased out by 2050. So how do we make them part of the carbon neutral system? And this is a great paper in that sense. I loved reading it. Hopefully this podcast is helpful to you as well. Okay, see you in the next topic, which should be, let's see, what will it be? It's a nice topic. It's called science-based risk for corporations. I have a related podcast for financial institutions elsewhere, but we'll look at this in the next podcast. Okay, see you.